a little shorter than the module 10, but and somehow all that we would do here is just the same as we have done during our midterms. So hopefully, mas mabilis din siya i-digest. Ano? Okay, so we'll be discussing just two subtopics. For this module, we'll be discussing the angular momentum and the magnetic moment. Okay, so yeah, I know you have already heard this, and I think you got we have electricity and magnetism as part of your like physics coursework or not? Anong physics ninyo class? During second year college or first year ba? Nag-electricity and magnetism ba kayo?
Yes po, nung P6 to po.
Okay. So yeah, I mean, since we'll be kind of um, diving into this, so since we have angular momentum and magnetic moment, I think it would be better if ma-recall nyo siya. You know? So, but of course, we have the general hand rules. We have the right hand rule for the magnetic angular momentum, and we have the left hand rule for the magnetic moment, and pretty simple naman yun. So, but everything would really make sense if you could recall your physics too. Thank you for answering. Okay, so anyways, let's start with the angular momentum. So, intro before this one class, as we have already discussed, no, we know for a fact that n limits the values of L and L limits the value of M sub L, and we just can't have a 3D, a correct or an accurate 3D representation for those for those um, wave functions which has L not equal to 0, which has L a non-zero L, L is equal to 1, L is equal to 2. And another thing is we are only given from the last module, no, we are only given the conclusion that we could like kind of find the probability density of of the electron in that if in a hydrogen-like system, in that we could like kind of get a hunch on what the probability is of finding that specific electron in a specific area, and what would the radius be more likely be, and how would the electron be but the question is how would the electron be oriented in 3D space. So we need the vector part of that. So everything class that discussed we have discussed, you know, from the previous module is kind of like our scalar quantities in a sense, since they're not talking about the direction. But now we'll be looking at the directionality of things, especially for of the angular momentum and um, of the magnetic moment. So we'll look more deeply into the orientation in 3D space of these wave functions. Wait lang. And sorry, can you still hear me? Can somebody confirm before I continue? Okay, so yeah, as I was saying, and now so we'll be talking about the orientation 3D space. Actually, class your L, the quantum number L, gives us the what do you call this? The magnitude or the value, the magnitude of the angular momentum, right? So we know for a fact that there is a huge significance when it comes, I mean, regarding the orientation in 3D space, there's a huge um, significance between looking, I mean, uh, significance in using the angular dependence um, of the orientation of the electron. So, but we have to know that the L dictates the magnitude of the angular momentum and the magnitude of the magnetic moment, while the M sub L gives us the orientation of the angular momentum and the magnetic moment. Okay, so yeah, but they do come hand in hand, you know, since the L limits the M sub L, possible M sub L values. Anyway, so let's talk about the angular momentum first, and then cut lang tayo, break lang tayo before tayo magpunta sa magnetic moment. No? So the classical relationship between angular momentum and linear velocity is illustrated in the figure on the left. Suppose that a particle of mass m is undergoing circular motion in the xy plane in an anti-clockwise direction or counterclockwise direction if one is looking down along the along the z-axis. So I have here class a figure. If you're going to look, okay, along the z-axis, so coming from here, your eyes should be positioned here. If you're going to look at the z-axis, you would see that the electron is orbiting around the nucleus on the xy plane in an anti-clockwise direction or a counterclockwise direction. And as you can see, for example, class, when the particles on the x-axis at this point, this m is, the particle with the mass m. So when the particle is on the x-axis, you would see that the positive velocity, it has a positive velocity, uy in the y direction. So kung, syempre class, this is, of course, we are talking about linear, what do you call this? For velocity class, of course, we are looking at it in a um, specific position. So for example, for this rotation, so for this direction of rotation, if your particle happens to lie on the x-axis, you would see na yung direction niya would be parallel to the y-axis. Okay? So yun yung kanyang direction, and its linear momentum py is muy. Okay, so its angular momentum is then by definition positive along the z-axis and is given by L sub z is equal to L plus yung ating angular momentum, ha, capital L, is equal to Pyx, which is equal to Muyx. Okay, so Pyx, or the linear momentum, okay, linear momentum, and multiply natin sa x, which is yung um, layo niya from the origin. Okay, so and then we have, of course, since your momentum is just equal to mass times velocity. So kung ano man yung velocity niya, which is u sub y, u sub y, meaning na yung kanyang direction is along the y-axis. Okay, so times mass. So that's muy x. So the sign of the angular momentum is determined by the right-hand rule. So you just have to use your right hand. I just don't know if um, I think you're looking at my my reflection, right? So basta use your right hand. So I don't know kung left to sa inyo or basta this is my right hand. So if you're going to use your right hand rule, class, your thumb, aside from your thumb, the rest of your fingers should follow the direction of the rotation. So for this one, since the rotation is clockwise, anti-clockwise or counterclockwise, so sa right hand rule natin, nakataas yung thumb natin, right? Um, can you please open your cameras? So para kita ko as you do this. So yeah. So makikita niyo na naka-thumbs up kayo, right? After doing that, using your right hand. So yung right hand, can you please do this? So can you somehow open your cameras for me to be able to see that you actually do this? So sa right hand rule natin, you would see na pag kinlasp nyo siya, yung inyong hand, naka-thumbs up kayo. So sa right hand rule natin, this is only applicable class for the angular momentum, for the direction of the angular momentum. Can you still hear me? Like nobody's opening the camera. So I suppose hindi nyo ako naririnig. Or are you doing it like dahil ba sa net kaya hindi ko kayo makita? Ano, or tulog na ba kayo? So yeah, sa right hand rule natin for the angular momentum, huwag kayong malulito kasi ang magnetic moment natin is left hand naman yon. So for this one, since counterclockwise yung direction natin, naka-thumbs up siya. So you would you would expect na yung angular momentum natin would have a positive value. I mean, would give us would point us to the direction of the linear momentum vector. Okay, so yeah, so this again, so the curved fingers of the right hand are caused to point in the direction of the linear momentum vector, and the thumb, I mean the angular momentum vector pala, and the thumb then points in the direction of the angular momentum vector. Okay, so kapag counterclockwise, nakataas siya. Kapag naman clockwise, kapag right hand rule, nakababa yung ating angular momentum, yung direction. Okay, so next figure shows the situation when the particle is on the y-axis. A positive momentum px then means that it is moving in the clockwise direction, so that the angular momentum L is now negative ypx. So what if naman, sir, yung ikot ng electron namin or ng particle namin is clockwise? Okay, so kapag clockwise class, obviously, kapag clockwise yung ating kamay is ito-thumbs down natin, for you to be able to like curve your fingers, I mean, following the clockwise direction of the revolution, or revolution of the electron along the xy plane. So you would see that I mean, you would see na naka-down yung um, thumb along the z-axis, and that is the direction of your angular momentum. So we can generalize these results for a particle. This is negative yp sub x. Teka, mababa na yung tinaba ko. So we can generalize these results for a particle moving in any direction. So if its momentum components are px and p sub y, and its position coordinates are x and y, the resultant component of angular momentum along the z-axis is given by this one. So we have L sub z is equal to xp sub y minus yp sub x. So ito yung class. For example, if you have an electron, generally, so hindi given sa atin kung nagta-travel siya along, counterclockwise or clockwise. So class, always and always, isa lang yung kanyang tinutukoy na spin. So kung clockwise or counterclockwise, so we would know it. We just have to calculate for the total the angular momentum, and kung ano yung lumabas sa atin na more, kung alin yung mas mataas yung magiging value sa atin for this one, that would govern kung ano yung magiging direction ng ating angular momentum. Okay, so the corresponding quantum mechanical operator, according sa table 11.1 natin, so this, yung 11.1 table natin, you would find this sa module natin regarding the postulates. So after 6, so that's module number 7. Okay, so we have marami tayo dumang operator, but so far, at that point in time sa discussion natin, we were just able to use the x hat operator, right? Or the position operator, the linear momentum operator, p sub x, one dimension and then one-dimensional linear momentum, and then the Hamiltonian operator. But you would see na meron din dong mga LZ hat. We have the LX hat, LY hat. They are the angular momentum operators. Okay, so the corresponding again quantum mechanical operator as given in table 11.1 for the L hat Z or the angular momentum at Z-axis along the Z-axis is equal to h over 2 pi I times x, okay? And then first derivative with respect to y minus y times first derivative with respect to x. So in polar coordinates, this becomes this one. So we have L sub z, which is equal to h over 2 pi I times the first derivative with respect to phi. Okay? With respect to phi class, in a sense na ang x and y axis natin class, kapag siya ay kinonvert natin to a polar coordinates, would actually just give us the what do you call this? The phi coordinate. Okay? Kasi along the xy plane ang phi coordinate natin. No, and that would be simplified to h bar over I times the first derivative of whatever they call this the object is or whatever the wave function is with respect to phi. So where h bar is h over 2 pi. Okay? So exactly the same type of treatment can be applied to the components of angular momentum along the x-axis and the y-axis. Okay, so leading to expressions for the operators L hat x, L sub x hat, and L sub y hat. Of particular significance is the square of the total angular momentum operator. So for this one class, we are just kind of looking at the summation of the square of the angular momentum along the x, y, and z axis. Okay, so that is L hat square is equal to L sub x square hat square plus L sub y hat square and L sub z hat square. Okay, so this is given by L sub hat square, which is equal to negative h squared over 4 pi squared. As you would see class sa table 11.1, pare-parehas naman sila. Same lang, like h over 2 pi I. Magbabago na lang sila class sa kanilang dependence sa phi or sa theta. Okay? But obviously, phi and theta lang sila naka-depend, no? So that would give us this expression. So negative h squared over 4 pi squared multiplied so 1 over sine theta times the first derivative of sine theta times the first derivative of the wave function yan with respect to theta plus 1 over sine squared theta times the second derivative of any wave function with respect to the phi. Okay. So we saw in our discussion of postulate 3 that if two operators are such that they have the same eigenfunctions, the corresponding physical properties can be measured simultaneously and precisely. Tama ba? Sa postulate number 3 natin. And kinakalculate natin siya. Chine-check natin yung... Actually, of course, what we are talking about here is if the operators are commuting or not, right? So yun lang naman yung pinag-uusapan natin sa postulate number 3. And we will now show that the operators h hat or the Hamiltonian operator, the angular momentum operator, and the square of the angular momentum operator have the same set of eigenfunctions. This means that, again, kapag commuting sila, the energy, the component of angular momentum along the z-axis, and the square of the total angular momentum can all in principle be measured simultaneously. Class, yung ginamit natin for this one is the z-axis. Actually, arbitrary lang siya. Pwede nyo naman siyang i-check sa x-axis or sa y-axis. But then, class, of course, yung L sub x, L sub y, and L sub z, they are not commuting with one another. So hindi natin pwedeng like sabay-sabay lang sila. What we are trying to do here is we are proving that h hat, L hat, and L sub x hat, so L sub y or L sub z hat. So kahit alin yung piliin nyo doon, basta isa lang yung pipiliin niyo. And L sub square hat ay commuting. Piliin lang natin sa z-axis. So wala lang, arbitrary lang. So but you can use the x-axis or the y-axis and then treat it the same ways. Parehas lang yan. Okay? So yeah, and the square of the total angular momentum can all again in principle be measured simultaneously. So the operator LZ hat involves only the angle phi And the function, this one yung ating function, ay solution to ng Hamiltonian equation natin. So we have v is equal to 1 over square root of 2 pi times e raised to I times m sub L times phi. Okay, so this is the solution of the h hat equation or the Hamiltonian equation that involves phi. Okay, so this function is therefore an eigenfunction for h hat. So since kung gagamitin natin class h hat and solution siya ng h hat, meaning basta may solution, eigenfunction yun, no? That would return, I mean, the operator would return as the phi equation, okay, and that would give us an eigenvalue, okay, and we will now see if it is an eigenfunction of L sub z hat. Class, you do not really have to use the the commuting notations that we have. I mean, just to calculate if they are actually commuting, you could like use an eigenfunction. And since commuting um, operators share the same eigenfunction, so if for example for this one, the Hamiltonian equation has this function as its eigenfunction, it should also follow that these eigenfunctions should also be an eigenfunction of L sub z hat and of L squared hat, right? So all because we're trying to prove that they are indeed according to postulate number 3, commuting. Okay, so yeah, so we just have to use this operator and act this upon the given wave function. Okay, so we have L sub hat, LZ hat, L sub z hat. Okay, operate acting upon the phi equation. So that would give us h over 2 pi times this the first derivative of the phi equation, okay, with respect to phi, which would give us h m sub l over 2 pi times 1 over square root of 2 pi e raised to I m sub l phi. So we have L sub z, and this one class is the same as your phi equation, right? So this operator returned as back the phi equation. So, and that give us h m sub l over 2 pi as the multiplier for this one, which is also our eigenvalue. Okay, so your L sub z hat acting upon the phi equation gives us m sub l over h over 2 pi times times the returned wave function, which is equal to m sub l simplified multiplied to h bar, which is equal to h over 2 pi times m sub times the phi equation. Okay, so the function phi is therefore an eigenfunction of L sub z. Okay, as well as of h hat. Okay, so eigenfunction siya ng angular momentum along the z-axis and ng Hamiltonian operator. And the eigenvalue of the angular momentum operator along the z-axis is equal to m sub l h bar or m sub l h over 2 pi. Okay, so yun yung eigenvalue niya. So this expression therefore gives the quantized values of the z component of the angular momentum. Angular momentum. Sorry, payagan nyo na ako. Nasa-stress ako mag hindi okay yung sinulat. The operator L hat square involves only, so we're done with proving that the Hamiltonian operator and the angular momentum operator along the z-axis are indeed commuting, right? So we just have to look if the L square is also commuting with them. So it involves only theta and phi, and we know that the function theta phi, okay, is an eigenfunction for the Hamiltonian operator as well. So we know, class, for a fact that the Hamiltonian operator is a wave function. Is an operator that could act upon the radial equation, the phi equation, and the theta equation. And since phi, theta, and the radial equation, they are all orthogonal with one another, then we know for a fact that combinations of these wave functions are also eigenfunction of specific operator, right? So it only means that the wave function of phi multiplied to the wave function of theta is also an eigenfunction of the Hamiltonian operator, right? So we may therefore see whether it is also an eigenfunction of L hat square. So we have L hat square times the wave function theta and phi. That would be negative h squared over 4 pi square times yung ating phi sine theta. Multiply natin sa first derivative with respect to theta ng sine theta times the first derivative of theta with respect to theta plus yung ating theta over sine squared theta multiply sa second derivative of the phi wave function with respect to phi naman. Okay? So the comparison of this equation with theta, phi equation and the theta equation shows that the function in brackets in equation 11.10, this one, class, yan, itong bracket na to, has the eigenvalues L multiplied to L plus 1. Kung babalikan natin, class, yung discussion natin regarding this part, we know na this one has an eigenvalue, no? So yung eigenvalue is L plus 1. And then that would bring us back yung ating wave function. So yeah, and may therefore be written as L times L plus 1 times the wave function, the product of the wave functions phi and theta. So we have discussed this, kailan to discuss? Module 9, right? Okay, so yeah, so we got this. So we have the operator L squared hat acting upon the product of the wave function of theta and phi that returned us back the wave function, the product of the wave function theta and phi, and gave us this eigenvalue. We have L times L plus 1 times h squared over 4 pi squared. Okay, so I mean considering yung ating L hat square. And then that could be simplified to L times L plus 1 times h squared, and then yung ating wave function. So the eigenfunction for the Hamiltonian is therefore also an eigenfunction for L squared. So with the with this eigenvalue. Okay, so tatanggalin nyo lang naman. So we have thus proved that it is possible to make simultaneous and precise measurements of the total energy, the total angular momentum, and the component of the angular momentum along the z-axis. So this arises because the operators, again, h hat, L sub z hat, and the L squared hat commutes according to postulate number 3. Wait lang to. Class, wait lang ah. Can we take 5 minutes before, I mean, a 5-minute break before tayo mag-dig in sa last natin topic, which is the magnetic moment. Wait lang.
Okay po.
Now back to wave functions. Each wave function for z are x, y, and at Hilbert are or three-dimensional for y and y or z and z. These basis vectors are linearly independent, so we order 0 products are always good and them give us the z vector, and so vector in a Hilbert space, just like x, y, or z are vectors in your everyday Cartesian space. Everything we just said about x, y, and z can be applied to the set of wave functions that comprise that Hilbert space. The difference is that a quantum system may be described by a large number of wave functions, much more than 3, all of which are orthogonal with each other, and they are also linearly independent three-dimensional vectors. It's time to use n to introduce picture with to have the Cartesian components are orthogonal, so their linear projections or dot products are always 0, and z as well as y and y or z and z.
Hi class. Sorry. I just had to attend to something urgent. Anyways, so let's just make it quick since we do not have enough time. So we have the angular momentum. So yung angular momentum that we have already discussed. We just have to use the right hand rule for that. So yung angular momentum natin is going upward. So, for example, for along the z-axis, if counterclockwise yung ikot ng ating electrons, and for clockwise direction, down naman siya. The reason, class, why we have to know that we have to know the direction for the angular momentum is because yung angular momentum kasi natin, class, yung direction natin for the angular momentum, can you hear me? Amidst the chaos. Can you? Okay. So again, yung angular momentum natin, yung direction ng class is always opposite the magnetic moment. Okay? And sir, bakit ba natin inaaral itong direction nila? Kasi class, we have to know for a fact that since we know na yung energy natin, the angular momentum could actually be calculated simultaneously, right? So ibig sabihin, somehow dun sa hydrogen-like atoms, nakadepende lang yung energy niya sa radial equation, right? But for those na hindi hydrogen-like atoms, which is mostly the case for most of the atoms, hindi sila sumusunod doon at meron tayong pagbabago sa energy natin upon considering those which, kasi sa principal quantum number lang, di ba, nakabata yung ating energy sa hydrogen-like atoms. But for the rest of the atoms, which is most of our atoms, nakadepende tayo sa angular, meron tayong angular dependency na tinitingnan. So what we are looking here para mas mapaikli and hopefully mas mapadali sa inyo, yung angular momentum natin lagi siyang opposite sa ating magnetic moment. And since yung ating magnetic moment, class, and of course yung ating angular momentum, ay doon nakadepende din yung ating energy, kailangan malaman natin if yung ating bang z-axis goes, for example, for z-axis, goes along the magnetic field, dun sa field natin. If it goes along with that, mababa lang yung energy niya. If it goes against that, so yung kanyang energy ay mataas. So ibig sabihin, even though pare-parehas lang sila ng n, ng number ng principal quantum number, actually in reality, hindi sila same ng energy. You know, hindi degenerate yung kanilang energies, and pwede natin silang at makikita natin yon, ano, by checking yung kanilang magnetic moment at kung parallel ba with that or anti-parallel with that yung z-axis natin or yung kahit anong axis natin tinitingnan. Okay? So for this one, again, the magnetic moment, an orbiting electron, I only have 5 minutes, being charged generates a magnetic field. Kapag meron kang isang orbiting kahit na ano class na moving na charge particle, of course may magnetic field yon. Since the electron is negatively charged, the direction of the magnetic field is exactly opposite to that of the angular momentum. Okay? So laging ganun ha, kasi negative charge ang electron natin. So lagi siyang nakabaliktad. So pwede mong tingnan na lang yung angular momentum, and then obviously nasa kabila nun yung iyong nasa opposite side nun ang direction ng yung call this yung magnetic moment. Or pwede mong tingnan yung magnetic moment. Ang ginagamit naman natin is left-hand rule. So kapag counterclockwise yung ikot ng ating particle ng electron, so nakababa yung ating magnetic moment. Okay? So yung angular momentum natin nakataas naman pag ganun. Kapag naman clockwise, naka-up naman yung ating magnetic moment. Okay? And then nakababa naman yung ating angular momentum. Okay? So yeah, yun lang naman yun. Pero obviously similar lang, class, yung magkaiba lang sila ng orientation pero similar lang yung treatment natin for magnetic moment and for angular momentum. So again, there is quantization and precise and simultaneous measurements can be made of the energy, the component m sub z, yung kanina L sub z yung gamit natin for the angular momentum along the z-axis. This one naman is the magnetic moment along the z-axis. So m sub z of magnetic moment along the z-axis and the square of the total magnetic moment. This arises because the magnetic moment operators m hat square, m sub z hat, commute with the Hamiltonian operator, the L sub z hat, and the L squared hat, or the angular momentum operator, and therefore have the same set of eigenfunctions. So the same quantum numbers L and M sub L therefore relate to the magnetic moment. Okay? So ito class yung itsura ng ating angular momentum kanina. Ito naman yung ating magnetic vector. So kung ang orbiting electron natin is counterclockwise, it says ang angular momentum natin is up at ang magnetic moment natin is down along the z-axis. So ito naman class yung itsura kapag naka-3D na sila. So ito yung ating kapag ang orbiting electron natin class is clockwise naman, makikita niyo yung ating magnetic moment is up and yung ating angular momentum is down. Okay? So yun. Ito, i-discuss naman natin sila. Okay? So the importance of the magnetic moment class is that it dictates the orientation of the orbital in a magnetic field. So yung magnetic moment class ay nagbibigay sa atin ng orientation sa magnetic field. Kung yung magnetic moment ba natin would be like, kasi we want to know kung along the parallel or anti-parallel siya with the magnetic field, right? So which may be due to neighboring atoms. So meron tayo ditong figure, shows one arrangement that can arise when a p orbital, L is equal to 1, is in a magnetic field along the z-axis. So the z component of the angular momentum and of the magnetic moment opposite to one another must have quantized values corresponding to the magnetic quantum number m sub L along the z-axis. Mamaya ko nang babaguhin. In the case shown in this figure, the z component of the magnetic moment, yung z component natin, is aligned with the field. So yung positive z natin, class, ay naka-align siya sa magnetic field natin. So naka-positive yung ating magnetic field sa z-axis natin. So for this one, which means that the z component of the angular momentum is aligned against the field. Yung angular momentum naman natin, naka-against naman siya sa ating, of course, sa ating field. This is the case of m sub L is equal to -1. And since the magnetic moment is in the same direction of the field, the energy has its lowest value. So for m sub L is equal to -1, yung z component natin ay positive. Yung positive z component natin is aligned along dun sa ating magnetic field, which is a good thing kasi kapag ganun, ibig sabihin mababa yung energy natin. So that means that m sub L is equal to -1 is actually of lower energy compared sa iba nating m sub L of the same na L. Okay, so another possibility is that the component L sub z of angular momentum is aligned with the field. M sub L is equal to +1 naman. And the magnetic moment is against it. So this corresponds to the highest energy naman kasi nag-o-oppose siya sa magnetic field. So a third possibility is that L sub z is at right angle, so naka-perpendicular siya dito to the field. So this corresponds to M sub L is equal to 0, kulang, and to 0 energy of interaction. Kasi naka-parallel siya, ay naka-perpendicular siya. So ito yun. And makikita ninyo, wala tayong interaction for this one. Wala dito yung particle. So ito yung, kumbaga, node, hindi mo siya dyan makikita. Parang ganun, okay? So between the magnetic moment and the field. Okay? So another thing, ito meron tayo dito for the d orbital naman. Anyway, so the L sub x and L sub y components of the angular momentum and the m sub x, I think this is the last slide, and the m sub y components of the magnetic moment do not have precise values. And the angular momentum and the magnetic moment therefore precess about the z-axis, as shown in the figure, this figure on the right. This motion, which corresponds to the curved surface of a cone, keeps L sub z, M, and M sub z fixed, okay? But leaves L sub x, L sub y, M sub x, and M sub y indeterminate, right? All because, class, we know for a fact na kung ang L sub z natin is, for example, L sub z yung tinitingnan natin kasi yung z-axis, we know for a fact na sa Hamiltonian operator natin, sa L square natin, siya ay commuting. And hindi siya commuting with the L sub x and L sub y. So hindi din dapat commuting si M sub x and si M sub y with M and M sub z. Got it? So figure shows this one, the situation for the d orbital. Sorry, bigyan niyo ako kahit 5 minutes. for the orbital for which L is equal to 2 and M sub L can have the values of -2, -1, 0, 1, and 2. So the diagram shows the angular momentum vectors. The magnetic moment vectors are not shown para lang hindi medyo complicating. Pero obviously, class, kung ang direction ng magnetic field natin is upwards, yung ating kung ang magnetic moment natin is upwards, yung ating angular, asan ba ang angular momentum natin? Is it given? It shows the angular momentum vectors, the magnetic moment vectors. Basta opposite man sila. Sorry. Opposite naman sila lagi. So the case for M sub L is equal to negative means that the angular momentum has its maximum value in the direction opposed to the field. Binigay ba class ang direction ng Direction ng L for this one? Hindi ko alam. Tama ba? Ito ba yung figure na dapat natin tinitingnan? Anyways, so basta class, kapag nag-go sila along sa positive z-axis, yung ating magnetic moment, yun yung pinakamababa yung energy. And kapag nag-oppose siya doon, yun yung pinakamataas na energy. Okay? So, obviously, kaya mo nang i-rank yung -2, -1, 0, 1, and 2. Okay? So, yeah, the case of M sub L is equal to -2 means that the angular momentum has its maximum value in the direction opposed to the field. And the magnetic moment then has its maximum value in the direction of the field. So align siya sa field. So this corresponds to the lowest energy for the system. And the highest energy is for M sub L is equal to +2 kasi nga nasa kabila siya, naka-oppose naman siya yung ating magnetic moment sa positive z-axis or sa magnetic field natin. And M sub L is equal to 0 gives zero interaction. Ito yun yung pinaka nasa gitna. Okay? So yun lang class. That's just it. Our kumbaga, take-home message from this one is that the magnetic moment and then the angular momentum, which is being governed to us by the M sub L and the L values, they actually contribute to energy, and not just that they gives us the orientation in 3D space, but they actually give us a glimpse of what it actually looks like for those which are not a part of the hydrogen-like systems. So, which is mostly the atoms that we have, in the natural world. For example, we have helium, carbon, na hindi naman mga ionized, hindi hydrogen-like. So, ganito yung itsura nila. And hindi natin aasahan na sumusunod sila sa principal quantum number lang. And you would know it, class, kasi by now alam nyo naman na yung ating notations, electronic configuration. For example, we have 1s, right? Next is 2s, and then we have 2p, and then we have 3s, right? And then we have 3p, and then we have 4s, and then we have 3d. So kung ang susundin sana natin is mas mataas dapat ang ang energy ng n value, sana nauna ang 3D orbital kaysa sa 4s, right? But then hindi nga yun yung case, all because of the magnetic field, the magnetic moment and the angular momentum, which is very important for us to be able to see and understand. So, do you have any question, class, regarding this? I'm so sorry. Sobrang gulo ngayon talaga sa lugar namin dahil sa daming construction. Yeah, do you have any question regarding this one? Nakuha nyo naman ba yung point? Like, do you get it? Bakit ba natin kailangang pag-aralan to? Okay naman? A question. Go ahead. Yes. Yes. Same lang sila lahat. I mean, same na operator lang siya. Magkaiba lang sila kasi yung mga operators ng class ay vectors. So meron silang direction. Pero pares sila ng magnitude. Yes. Kasi ang magnitude ng M, ng magnetic moment, tulad ng sinabi ko kanina, ang magnitude ng magnetic moment at ang magnitude ng angular momentum ay govern ng L. Ang M sub L ang nag-govern ng orientation nila. So, ibig sabihin, parehas lang sila ng treatment, parehas lang sila ng operator, ng ginagawa sa operator, magkaiba lang sila ng direction. Got it? Any more question? Okay lang, class? I-edit ko yung mga lakas tayong oras. Anyways, isasend ko to